Hello, welcome to this screencast about the degrees of freedom of a vessel. So first look at the axis of a vessel. We start with the z-axis of the vessel, which is pointing vertically upward. Then we have a y-axis over here, and moving forward we have the x-axis. So x, y. Important is if you move the x-axis toward the y-axis, you'd go in the direction of the z. Well, that's alright. So this is the positive y, positive x, and positive z. When we look at the 6 degrees of freedom, we can split them into 3 rotations, and we have 3 translations. Okay, we'll have a look. First start with the x-axis. If we rotate around the x-axis, that would be something like a roll. When we move forward around the x-axis, that's the surge. Around the y-axis, when the vessel is rotating around the y-axis, that would be pitch. And moving sidewards is sway. Then we have the z-axis, and the rotation about the z-axis is yaw. And the translation would be heave. Okay, so far so good. Next thing is that we would describe the rotations and translations as a differential equation, or put the rotations and translations in a mathematical equation. So the translations can be described with a mass spring system. Say you have a spring and a mass over here. Spring has a stiffness k. You could say that the differential equation of a translation would be something like a times the second derivative of x added by b times the first derivative c times x is a force. If you describe this as the z-axis, of course it would be a times the second derivative of z, b times first added by c times z equals another force. So this would be your mass, this would be your resistance, and this would be, in our case, your stiffness. Okay, let's have a look at the rotations. Well, the rotations are slightly different. Imagine a pendulum. We have a mass on a cord, and it is moving forward, backward, this way and that way, and we're interested in the angle over there. So this is a mass, and it has a length of L. Okay, how do we describe the differential equation? It doesn't fit over here, so I put it over here. So the differential equation would be something like the moment of inertia times the second derivative of the angle added by n times the first derivative. So this would be something like dampening added by, in our case, displacement times gm of the vessels times the angle, and that would equal a moment. So later on we will work out these differential equations, but so far this video we have a differential equation for translations, and we have a differential equation for rotations. Thanks for watching.